10 to 1 by s tends. Okay, so as s tends to 0, this tends to 3, this tends to 3, this tends to 5, this tends to 1 by 15. So s tends to 0, ss tends to 1 by 15. Okay. Now ss tends to say some value closer to 3. Yeah, s tends to very high value, say infinity. Then ss tends to, that is divide everything by s, it's also by s. So as s tends to infinity, 1 by s tends to 0, this cancels, this become 1 plus 3 by s. So this also tends to 0, so no denominator is 1. Numerator as s tends to infinity, 1 by s tends to 0. So this tends to 0. So this is basically, it passes with an attenuation 1 by 15 here, and eventually at infinity this goes to 0 value. So we don't know exactly whether it is a low pass filter, but we know that at low frequency it passes it. It may have some other notch or what it is, but we know at low frequency it gives an attenuation 1 by 15, and at 0 it doesn't allow the as equal to infinity, it doesn't allow the signal to pass through. Okay, so as let us take some intermediate values. So 1 by s plus 3 into s plus 5, as s tends to say 3, this can take 6, 8, right. This is 1 by 48, even lesser than that. And if we give different values, since this is a function of s square, this will not be linear, and hence it will have some ripple, and it is basically decreasing to some value. So this will have a response. 1 by this square, 1 by square by s plus 15. This will have a response with some ripples. Okay, now let us see how the design comes. If SS is 1 by s plus 3 into s plus 5, this can be written as the difference between 5 and 3 is 2, so we can put 1 by 2 into, you are basically making it into partial fraction. So 1 by s plus 3 minus 1 by s plus 5. So when you take the LCM, s plus 5 minus s plus 3 will be 2. So that 2 will cancel with this, and denominator you have s plus 3 into s plus 5. So this is your HS. So if you want to implement this, 1 by 2 into 1 by s plus 3 minus 1 by s plus 5, or you can write this as half by s plus 3 minus half by s plus 5. So how will you implement this? You go for, you can just replace Z I, or if you go in the procedure way, this you take the inverse unilateral Laplace transform of this, so that become 1 by 2 into e raised to 3t ut basically. So if it is unilateral Laplace transform, you need not write that, half into e raised to 5t. So this is ut. So suppose your sampling time is equal to 1 second. sampling time may change with respect to your signal. So if you are taking a speed signal, it require at least the Nyquist criteria for that is 4 kilohertz. So you require at least 125 microsecond for TS sampling time. So let's assume that C is 1 second. In that case, this can be written as UNT. This sample version can be written as half into e raised to 3n capital T minus half into e raised to 5n capital T. So capital T is 1, so half e raised to 3n minus half e raised to 5n. So this is basically half into, if you take h set from this, you take the set transform of this. So if you take the set transform, you consider it as e raised to 3 e raised to n un, because we are taking unilateral set transform. So this becomes similar to a raised to n un. Its set transform is 1 by 1 minus a set inverse. So this you can write as, these two terms you can write as half into by 1 minus a is basically e raised to 3 set inverse minus half by 1 minus e raised to set inverse. So this is your set transform. So 1 half by 1 minus e cube set inverse minus half by 1 minus a raised to 5 set inverse. So if you go for the implementation of this set, it's basically you have a half multiplier common to all, so you can put that half here. And then you go for two terms which are added together. So x set is this, plus you can put it like this. So you have two terms added together. So basically, let us write this as y set by x set. H set is y set by x set, so that is half by 1 minus e cube set inverse plus minus half by 1 minus e raised to 5 set inverse. So if you expand this, you cross multiply with this, so it becomes yn minus yn e cube set inverse become yn minus 1. So basically become yn minus 1 yn minus yn minus 1 e cube plus again yn minus 1 e raised to 5 is equal to half of xn. No, this you cannot write like this, right? You have two functions here. Okay. Or otherwise we can implement each of them individually. So let us not do like this, because you have LCMs, you need to multiply this together and take to the side. So okay, you can do like that also. Okay. So let us multiply this. To take LCM, this become e raised to 5, e raised to 3 minus e raised to 5 this minus this would be e raised to 3 into set inverse by 2 into, am I right? 1 minus multiply these together, e raised to 3 is 5, so raised to minus 2 minus e raised to 3 plus e raised to 5 set inverse. Okay. So this you can write as e raised to 3 minus e raised to 5 into set inverse by half of this by 1 minus this you can write as e raised to 8 set raised to minus 2 plus a plus e raised to 5 set inverse. So this is basically y z by x z. So you can write this as yn. You multiply with 2 also, 2 yn minus 2 e raised to 8 yn minus 2 plus e raised to 3 plus e raised to 5 yn minus 1 is equal to x of n minus 1 multiplied by e raised to 3 minus e raised to 5. So let us assume that e raised to 8 is some c1, e raised to 3 plus e raised to 5 is some c2, e raised to 3 minus e raised to 5 is some c3. In case it can be written as 2yn. E is basically 2.8. This exponentials are some constant. So 2yn minus 2 e raised to 8. You can put c1, so c1 minus y minus 2 plus c2 y and minus 1 equal to c3x minus. When you go for implementation, this is basically y is divide everything by 2, so this becomes c2 by 2, 2 by 2. So yn is basically c1 minus c2 by 2 y and minus 1 plus c1 y and minus 2 plus c3 by 2 x and minus 1. So if you go for the implementation of yn, to get yn you need xn. You take xn, you take the xn with a delay. So if you have xn with a delay, it becomes xn minus 1. Then that is multiplied with xn minus 1 is multiplied by c3 by 2. That is added with the previous values of yn. So if this is yn, you take delayed version of yn, put a delay here, that is yn minus 1, this is yn minus 1. Again you multiply it with minus c2 by 2. You have to add it with yn minus 2. So you take a delay again. This is your yn minus 2. So from yn minus 2 you multiply it with c1. After multiplying it with c1 you add it with this, and everything you add with x and minus 1, c3 by 2 into x and minus 1, which is coming here. This point is c3 by 2 x and minus 1, and all these are added together to form y. So this is the digital implementation of of the SS 1 by s square plus 8s 15. Okay. Is anybody trying to tell something? Okay. Okay, Abhishek, do you want to tell something? Or you can unmute. So mute the audio. Yeah. Okay. Now, so these are the basics of our filter designing of using impulse invariance method. So this kind of unlock filter, how do you normally design? You go for the this design may be obtained by the given ripple values, etc. So it could be a second order filter if you don't need that much attenuation, and if you have lower order, you know that these will not be that much steep. So if this is if that much steep transition is not required for you, second order filter may be okay. So in that case, this is how you implement it in the digital filter. Okay. So yeah, this what we have seen is impulse invariant method for digital filter designing from analog filter or transformation from S to Z. So basically, we saw yesterday that ZI is transferred as, or the basic transformation is ZI you put as e raised to SIT, where capital T is the sampling time period. Okay. Um, so that's all. So I think with this example, it would be clear for you. So next class we'll see what is bilinear transformation, which is another method using which some the S is mapped to Z. So we shall see this method and do a problem from this in the next class. Okay. So I think we can stop today's session. I'll stop sharing now. Okay,